Alright, first thing we're going to do is review Newton's laws. You should all be familiar with these, but the first law deals with inertia. And inertia is the tendency for an object to keep its current motion or to resist its change. So if you remember last year with the hovercraft, if you are sitting on the hovercraft and you give the person a push, they'll continue the entire length of the hallway with nothing else interacting with them. So after the initial contact, the object just continues to stay in that current motion until it interacts with something. So if you're headed straight towards a wall, you're going to hit the wall, right? Because nothing can change that path, that straight line path. Okay. The first law also has to do with no acceleration. So the simplest way to state Newton's first law is that balanced forces cause no acceleration. First law deals with equilibrium, so that means everything has to be balanced. It's basically another way to say the forces are balanced. With the first law, the forces can only act on one object, and that's really the most important part for Newton's laws and how to apply them when solving problems. Okay, so when we draw our free body diagram, look at a simple apple on a table. Okay, so here's our apple. Okay, so we have our forces. The forces that are acting on the apple, and that's what's important. Notice that as I have these labels, if you can see them, it says the force of what object it's interacting with. So the obvious one is that gravity is pulling on the apple, and that's pulling it down. So it's the force of gravity on the apple. The apple's not accelerating downward because there is a balanced force acting upwards, and that is because it's interacting with the surface, so the table exerts a force on the apple. And this is the important part. If you can say that both forces act on the same object, it could be an application of the first law. If when you say the force out long ways, they act on two different objects, you cannot be applying the first law. The simple mathematical expression is, of course, that the sum of all forces will equal 0. And this comes in relationship to the second law, which is the sum of all forces equals the mass times the acceleration. However, if the forces are balanced, there can be no acceleration. So A is 0, sum of all forces have to be balanced 0. Simple. Some extra little note here for inertial reference frames. It means that an object can be moving but not accelerating. Okay? So that's another example of the hovercraft. So key terms to make sure that you pay attention to is you'll see constant and uniform, but the key word there is speed. All right? If it says constant speed or uniform speed, then we know that it's the first law. Since constant means not changing, uniform will also mean not changing. So a non-changing speed, no acceleration. Has to be first law. Alright, the second law is the opposite of the first. First law is balanced forces do not cause acceleration. So second law is unbalanced forces cause acceleration. Right? Now I wrote this down a while ago. Those three dots actually mean therefore, I think. It's a mathematical notation. I'll figure it out later exactly what it means, but I'm pretty sure it means therefore. So unbalanced forces therefore accelerating. The important part here is that the acceleration is only in the direction of the unbalanced force. I don't know why this gets confusing to people. However, in the equation itself of F equals ma, the sum of all the forces is a vector addition. Whenever it's a vector equation, there has to be a vector on each side. Here the vector is acceleration. So think about it this way. The direction of the acceleration, since it's the vector, is going to have to be the same direction as the unbalanced force. That's really what those symbols are saying there. As is with the first law, all forces have to act on only one object. Okay? So again, looking at the apple, if we remove the table from underneath it, there will only be one force acting on the apple, force of gravity down on the apple. It's going to accelerate because it's unbalanced. If we want to include another force, such as air resistance, well, if we drop it too close to the ground, we'll have the force of air on the apple, and it will be much smaller than the force of gravity, still unbalanced. Notice the downward force larger than the upward force, the acceleration in the direction of the larger force. It's pretty simple. All right. So again, two key things. First law, second law, only one object. Now we have the third law, which last year we did not have to apply to problems very often. However, now we do. It's a very important concept when you have multiple objects interacting with each other in the problem. It really is useful when we have coupled type of motions, where two blocks are maybe in contact, moving under separate conditions. So like one will have friction, one will not, but the contact is still there. It can get very challenging to apply the third law correctly. Most people remember this as the action-reaction force. The improper way to say this is that for every action there's an equal and opposite reaction. That is actually not even the correct statement of science at all. The correct statement is for every action force there is an equal and opposite reaction force. It only talks about forces. Any other use of that statement is scientifically inaccurate and really is just talking about a cause and effect. This is not cause and effect. All right. The simple mathematical way to say that is a force of object A on object B will have an equal force that is opposite in direction of the force of object B back on object A. Very wordy. All right, so writing it as a math kind of equation is a lot easier. What's different with the third law? Why do we have the third law? This is when we have to look at two separate objects. The first law and the second law can explain every single thing that happens in our universe. All right, so the third law is always there. In order for there to be any force, there has to be two objects interacting. If there is no other force, no other object interacting with an object we're examining, there cannot be a force. If you think of an astronaut flying in the middle of deep space, very far away from any object, so that gravity becomes insignificant, there is nothing that astronaut can interact with in order to change its motion. So there is no force acting on that astronaut, or whatever you want to call it, floating around in space. So all forces arise due to the third law, which is an interaction between two objects. No interaction between objects, no force. All right, so we looked at an apple on a table as the first law, and an apple and gravity due to the earth for the second law. All right, so let's look at both of those situations under the third law parameters. So with the apple on the table, so the two objects that we're looking at are the apple and the table. From our original situation, we had gravity pulling it down and then the table pushing it up. So between the two objects, the first force we think about is the force of the table on the apple. So we have notice the force is drawn from the center upwards. So if the table is pushing upwards on the apple, there has to be an equal and opposite force. Now, the way that this is worded makes it super simple. We have A on B and B on A. The objects can't change. You have two of them. You can only mention those two. So here we have table on apple, so that means that the apple is pushing down on the table. Okay, so if gravity is pulling the apple down, the table's in its way, the apple's pushing down on the table, therefore the table pushes up on the apple. Okay, so that's one action-reaction force pair that's there. All right, so with the first law example, we had table on apple, gravity on apple. Okay, we just handled the one. So let's look at the force of gravity on that apple. So we can ignore that, we're ignoring the table now. So where does gravity come from? Gravity comes from the mass of the earth. So really, it's the force of the earth pulling down on the apple. So if the earth is pulling down on the apple, the reaction force to that would be the force of the apple pulling up on the earth. It's a gravitational attraction. Every object that has mass has gravity. So if the earth has a gravitational field, the apple has a gravitational field. Okay? And remember, it's equal and opposite. So the force that the earth is pulling down on the apple is equal to the force of the apple pulling up on the earth. But the reason why we don't notice that the earth is being pulled up is due to the mass. So since the forces between the apple and the earth are the same, the difference here is that when it's the apple, we have a very small mass. When it's the earth, we have a very large mass. So since the force is the same, that means the mass and acceleration product over here on this side has to be equal to each other. So if we have a very small mass, we have to have a very big acceleration. And if we have a very large mass, we will have a very small acceleration. All right, so we don't feel the earth flying up towards any object we drop. Okay, the acceleration is so small due to the very large mass. And so these are the basics. You have to think about the basics because we're going to have some very complicated situations. And if you think past what the basics are telling you, it makes it much more difficult to apply. All right, so that's just the first review of all three laws. I'm going to see if I can get another video together with some example problems.